All right, guys, let's talk about Bronsted-Lowry acids and bases. This is another definition of acids and bases. It kind of encompasses the Arrhenius model in many ways. It's similar to it, especially with the acids, but it's also a little bit different, especially in terms of the bases. Okay, so what we are looking for mostly, well, exclusively actually, in Bronsted-Lowry acid-base chemistry is the movement of protons. And we're going to use this word proton and hydrogen ion kind of synonymously, because hydrogen as an atom, when it loses its electron to become a positive one oxidation state hydrogen atom, all that is a naked proton, right? So protons and hydrogen ions are kind of the same thing. So we'll use those terms together. So the way Bronsted-Lowry acids and bases work is that we gain and lose hydrogen ions from a chemical formula. Okay, and so we're just talking about the movement of a single hydrogen ion from one place to another. Okay, and so here's an example. As a Arrhenius acid, we would have thought, okay, those things contain hydrogen, and so do Bronsted-Lowry acids. They contain hydrogen, but that's not the defining feature of a Bronsted-Lowry acid, because a Bronsted-Lowry base can also contain hydrogen as well. So let's just take a look and see what happens here. And one thing I'll point out before we get too far into this is that a lot of these equations we're going to see have oxidation states as positives and negatives, or even oxidation numbers, because we work a lot with ions when we work with Bronsted-Lowry acids and bases. Okay, so take a look here. This compound here, this is an ammonium atom, NH4, that's a +1 oxidation state. Over the course of a reaction, let's just pretend that that ammonium ion loses one of its hydrogen ions. So the only change to the formula is that the amount of hydrogens is lower by 1, right? We went from NH4 to NH3. And the other thing you see happen, and it's pretty common in these reactions, you see a change to the oxidation state. So we went from a +1 here on this ammonium ion down to a 0 on an ammonia molecule, and that's what happens when you take away one of the positives. You decrease the oxidation number by 1, and so we're decreasing from +1 down to 0. Okay, and we call these things acids that give away the proton, and then it becomes what's called a conjugate base. And so the acid has this amount of hydrogens that will decrease by 1 to become a conjugate base. Okay, the base is very similar, except that it's the compound that ends up with the donated proton. So let's just say that, so we're looking at two separate things here, but we're just exploring acid versus base to begin with. But let's just say that the base, which starts out as HCO3 with a -1 oxidation state, let's say that that somehow picks up a hydrogen ion and becomes H2CO3. So the only change to the formula is our number of hydrogens from 1 to 2. And so the base is the compound that's gonna ultimately end up with another hydrogen ion to become what we call the conjugate acid. I like to think about this that what makes something acidic is the hydrogens, and so if you're adding hydrogens to a base, it becomes more acidic, becomes what's called the conjugate acid. Okay, so let's look at the full Bronsted-Lowry acid-base reaction between the base and the acid that we just talked about. So here's our ammonium, and here's our this is just hydrogen carbonate, which is ionic. got a funny formula for that one. But anyway, these two ions are going to go through this acid-base reaction where ammonium is going to give away a hydrogen ion to the base to create our conjugate base and our conjugate acid over here. So as you can see, the hydrogen has moved from the ammonium to the hydrogen carbonate, and then that becomes this H2CO3, and as a result we have the ammonium is deficient by one hydrogen from where it was as a reactant, and that's what we call our hydrogen or conjugate base. Okay, and you can see how the oxidation numbers change here. We've taken these two charged ions and then we've put them together to make two neutral compounds here. Make sense? Okay, so let's do a couple more of these just as examples here. So here is a carbonate ion and water. So let's just, so it's really tough. Well, here we can determine probably that the water is going to act as the acid because it's the only one with a hydrogen, but it doesn't have to be the case. Like in the next example we're going to do, both of these things have hydrogen. So hydrogen is not the defining feature of an acid in the Bronsted-Lowry definition, but in this case, the hydrogen is the only compound that can be the acid. Anyway, so the only thing that can really happen is that this one of these two hydrogen ions is going to come over here and hook onto the carbonate ion, and that is going to result in an OH negative. That was formerly the water, right? H2O became OH. Now with a negative oxidation state, and then the other compound that gets created is this carbonate picks up that hydrogen ion that was from the water. So this is now HCO3, and because we've added a positive hydrogen ion to this already negative -2 oxidation state, that -2 drops down to a -1 oxidation state, and that's important to keep track of those oxidation numbers. So the water started out neutral, meaning essentially that the two positives from the hydrogen were offset by the two negatives from the oxygen, but we lost one of those hydrogens, and so now the resulting compound is a negative charge. All right, so here we would have called this the acid. This would have been the base. It's what gets the hydrogen ion. The thing that picks up the resulting compound from the base picking up the hydrogen is called the conjugate acid, and this is now called the conjugate base. And I just abbreviated them: CB for conjugate base, CA for conjugate acid, B for base, A for acid. And by the way, the acid and base are always going to be on the left of the reaction, and the conjugate pair is going to be on the right as products. Okay. One more, here's H2SO4 and H2O. So here you can't really tell by looking at the formulas here what is the acid and what is the base. You know, H2SO4 is typically an acid, doesn't have to be, and I'll show you a couple of examples how that is the case. But in a lot of ways, many times you have to see the products of the reaction to determine which was the base and which was the acid. So let's pretend that we make HSO4, and that is a negative oxidation state. Okay, so we can see pretty clearly that hydrogen, H2SO4, we've lost a hydrogen to become HSO4. Okay, so where does that hydrogen go? It must tack onto the water molecule to make something called a hydronium ion, H3O. And since we've added a positive hydrogen ion to a neutral compound, its oxidation state comes up to +1. Okay, so in this case, if you're seeing the products, like if the products were given to you originally, then you can define which of these is the acid and base. And clearly we know that this guy gave away a hydrogen. That means this other thing was the thing that took the hydrogen, making this the conjugate base and this the conjugate acid. Okay, but let's just say for some weird reason, like if we had made, instead of HSO4 minus, let's say that we made H3SO4 plus and OH minus. So let's just say that these were the products of this reaction here. Then we would have had to rearrange our acid base and conjugate acid base pair, because here H2SO4 has actually gained the proton, which makes it the base, and water has given away the proton, which makes it the acid. So it's all really dependent on the products to then revisit and take a look again at the reactants to determine which is the acid and base. So rule of thumb is that when you're defining the acid and the base and the conjugate base and the conjugate acid, just know that the acid is what becomes the conjugate base. So here in this example, the acid became the conjugate base, right? H2SO4, HSO4. And then the base becomes the conjugate acid by picking up a hydrogen ion, okay? So that is Bronsted-Lowry acids and bases. It's all about just moving one proton into or out of a formula and making adjustments to the oxidation state. All right, good.